Hey everyone, and welcome. Today, we're going to jump into the unseen physics that runs everything from a rocket launch to a game of pool. We're talking about two really fundamental ideas, the center of mass and collisions.
So here's a question for you. What do these three things possibly have in common? I mean, they seem totally different, right? Well, believe it or not, all of these chaotic, powerful, and sometimes precise events are all dictated by the exact same, really elegant set of physical rules. And by the end of this, you'll see exactly how they're all connected. So where do we even start? Well, first, we've got to understand a system's secret balance point. You can think of it like an invisible anchor that controls its entire motion, no matter how complicated the thing is. This magic point is called the center of mass, or COM for short. And here's why it's so powerful. Instead of trying to track, billions of individual particles in a firework, we can just treat the whole thing as if all its mass is squeezed into this one single imaginary point. It's a massive shortcut, and it makes analyzing motion so much simpler. Now, for simple symmetrical things like a rod, the center of mass is exactly where you'd guess it would be, smack dab in the middle. But for less symmetrical shapes, like a cone or a hemisphere, it actually shifts over towards the heavier end. And the really cool thing is, physics gives us exact formulas to find this spot, so there's no guesswork involved at all. Okay, so knowing where the center of mass is located, that's one piece of the puzzle. But the truly amazing part, the part that's almost like a superpower, is the unbreakable rule that governs how it moves. This right here, this is the law of conservation of linear momentum, and you can think of it as the golden rule for the center of mass. In plain English, it just means this. Unless you push or pull on a system from the outside, its center of mass is going to keep moving in a perfectly straight line at a constant speed, period. It will not change its path. And this brings us to a really crucial distinction. An external force, like gravity pulling down on a firework, that can change the path of its center of mass. But the internal force of the firework actually exploding, it sends pieces flying all over the place, right? But the center of mass, it just keeps sailing along that same smooth arc as if nothing even happened. All those internal forces do is just shuffle momentum around inside the system. So, this all leads us straight into the most dramatic application of these ideas, collisions. Really, you can just think of a collision as a very fast and intense moment where momentum gets shared between objects. So, how do we describe different kinds of collisions? Well, we use a single number, E, called the coefficient of restitution. But don't let the name scare you. Just think of it as a bounciness score. That's it. It tells us how much of the energy from the initial squish gets returned as bounce-back energy. Now, if you look at this table, notice the one constant. In every single type of collision, momentum is always conserved. That never changes. The real difference between them is all about what happens to the kinetic energy. In a perfectly elastic collision, no energy is lost. But at the complete other end, in a perfectly inelastic collision, that's where things stick together, you lose the most possible kinetic energy. It gets turned into stuff like heat, sound, and, bent metal. All right, enough theory. Let's actually see how these concepts give us these incredible shortcuts to solve what look like mind-bendingly difficult problems. In one fantastic tutorial, the instructor uses this great little story. Imagine two particles. Let's call them Anjali and Rahul. They both start at the same point on a circle and start moving in opposite directions. The catch is, Rahul is moving twice as fast as Anjali. So the big question is, how many times do they collide before they both arise back at the starting line? And the shortcut here is it's genius. First, you add up their relative speeds. V plus 2v equals 3v. That number, 3, is the magic key. It tells us to divide the circle into 3 equal parts. Now, we just track what happens. For every unit of time, Anjali moves 1 part, while Rahul, being twice as fast, moves 2 parts. By just tracing their paths, you can literally count the collisions. And the answer is 2. They collide at 2 distinct points on the circle before they both simultaneously get back to where they started. A really complex-looking problem just solved with a simple, elegant picture. Okay, let's try another one. Imagine we launch a particle into the air. At the very peak of its arc, it collides with and sticks to an identical particle that was shot straight up to meet it. The question is, what was that original launch angle? So the crucial insight here is to understand the moment right before impact. The projectile at its peak has stopped moving up, so its velocity is purely horizontal. All its momentum is sideways. Meanwhile, the other particle was shot straight up, so all of its momentum is vertical. This is perfect because it means we can apply our conservation law to the horizontal and vertical directions completely separately.
And when we apply conservation of momentum, we find that for the two particles to stick together and move off in that specific way, their initial horizontal and vertical momentums must have been equal. This means the tangent of the launch angle had to be 1, and the only angle whose tangent is 1 is 45 degrees, or pi/4 radians. A beautiful, clean result. So, beyond solving tricky exam problems, why is this stuff so important? Well, it's because these principles are really the foundation of how we analyze and design for motion in the real world. So let's just connect all the dots one last time. We started with the center of mass, that single point that simplifies any object's motion. We learned that the momentum of this point is conserved. It's not going to change unless an external force acts on it. And finally, we saw that collisions are all about how that conserved momentum gets shared between objects, and that bounciness score tells us how much energy is lost in the process. And that leaves us with a final thought to test your understanding. Using all this physics we just talked about, how would you design the perfect car bumper for safety? Would you want a collision to be more elastic or more inelastic? Think about where you want all that energy to go. The answer lies in everything we've just discussed. Thanks for joining me.